So when we have a numerical data set, what we might be interested in describing is the central tendency. This gives us the idea of the middle of the data, which helps us in wording in terms of describing the expected value for our data set. We can then describe, if we have values, what we expect to come through. So in this video, we're going to talk about two measures of central tendency. We're going to talk about median and mean. So median is a location in the data set. It's a location representing the middle of the data. So what we want to do is have our data, and when we work with our data in these cases, what we want to do is make sure it's in order. So the data should be in order from smallest to largest. And then once it's in order and we have it all listed out, what we want to do is find the cutting point for the median, and that cutting point will make it so that we have 50% of the data below that number and 50% of the data above that number. Now there's two ways to go about this, and it will just depend on how many data values that we have. So data set A here, we have 5 values. And what I even do, I can't really show it on my screen, but I actually use my thumbs and kind of work from the outer edges to the middle. So what I mean by that, and this will be kind of weird, but is if I start with my thumbs on either side here, I'm going to move towards the middle, which will be the idea of kind of covering up one side at a time. So like covering up that 3 and 18, and then that 8 and 15. So moving towards the middle. And when you have an odd number of data values, you're going to be stuck at a single number. And that number is the median. So it's going to kind of create this barrier, and 12 is part of this barrier that separates the lower and upper half of the data. So if I get rid of those boxes, now I can see this even distribution of there's 2 data values on the left, 2 data values on the right. So we have this balance of number of data values on either side, and this would have a median of 12. So that happens with an odd number of data values. With an even number of data values, if I kind of do the same trick here, if you imagine those are my thumbs, and then I would cover up the 3, cover up the 20, cover up the 8, cover up the 18, and then what will happen is here we're going to be stuck at 2 data values. So this cutting point of the lower and upper half of the data is actually occurring between 12 and 15. And what we're going to do is actually average those values. So we're going to take 12 plus 15 and cut that in half. So our median for this case, coming from the average of those two numbers, would be 13.5. So then we could see in between those, the 12 and 15, we get this kind of barrier that evenly separates. So we have 3 data values on the left, 3 data values on the right, so it's holding balance. And then the median would be halfway between 12 and 15. So that's median. No real calculation to do. In fact, I try to avoid the wording of like calculate the median, doesn't really make sense. It's more find the median. So you just have to put your data in order from smallest to largest, and then in some way kind of move towards that middle until you end up at a value. If it's an odd number of values, it'll be an exact number as part of the data set. Even number will be an average of 2 of the data values. Now mean is a calculation. So mean is going to be the idea of an average. Those are the same things. So to calculate a mean, we're going to have this numerator and denominator. In the numerator, this is where you just add up all of the data values. And then in the denominator, we're going to divide by how many data values there are. Another word we use for this is sample size, which is just the number of values there are. So let's see this at work. So going back to dataset B, which we saw up above there, what we'll do is add up the numbers. So 3 plus 8 plus 12 plus 15 plus 18 plus 20, and then divide by, and we have 6 data values. So this will have a mean of, and I'm going to round to 4 decimal places here, just because we'll generally do that. When you make the sentence, you could round how you like we would say the average of this data set is about 13 if you wanted to round it to a whole number. But for homework and my open math, it's good to have the practice of rounding to 4 decimal places. Some notation you might see float around for mean. You might see this is called X bar. This is a symbol that's used for means coming from sample data. Another symbol you might see for mean is a Greek symbol, mu. These both represent means. We won't get too far into the difference between them. If you ever take statistics, you go much more into it. But just in case you're suddenly asked for X bar or asked for mu, it's just taking the average of the data set. All right, so if we have data set C here, what I did is I copied data set B exactly. All I did was I changed this last number here, just so that we could see what happens when we throw in, this is going to be an outlier. This is very different and separate from the rest of the data. So, and what we could do is compare it to our previous mean and see how it changes. So, for the mean, we're going to take 3 plus 8 plus 12 plus 15 plus 18 plus 205. And then divide by, and we have 6 data values. So when we calculate this, we should get a 43.5 out. And what you can see here is there has been a big change. Where we were at about 13 before, now we're at about 44 if we're rounding to whole numbers. So there was this big increase, whereas if we went back to medians and went to data set B, and imagine I had changed that last data value to 205, would the median change? No. In terms of being covered up, that 205 gets covered up just the same as 20 was. Since it's on the edges, the median kind of ignores any outliers or extreme values at the edges. And that's something we're going to talk about because that is important that it does that. However, the mean does not do that. The mean takes into account every single value as part of the calculation. So by adding that into the numerator, the mean and the average grew overall. So with this and thinking about the shape of data, what we can do is think about how this affects the relationship between mean and median. Now with data set B, comparing our mean and median, those were fairly close to each other. And this is kind of personal of how you determine, are they completely different or somewhat close? But I'll just kind of guide you with this one of those are fairly close to each other. And it's because this data is fairly balanced, in terms of having about 13 in the middle there, that 13 up to 20 has kind of a difference of 7-ish, and this has a difference of 10. There is just this balance and overall somewhat symmetric distribution. So let's talk about what happens to the mean and median, and actually, sorry, we're going to leave out mode from this, because the mode is just the peak of the graph. But what ends up happening is median, if I had to estimate where the median is for each of these graphs, I would just look at where the peak is. It might be a little different, but without any other information, without the actual data, if I had to guess where the median was for each of these, I would guess the peak. That's typically how it would balance out. So with skewed left distribution, it'd be over here with the rest of the data, and I'm using lowercase m to represent median here. In fact, I should write it out so that when I get to mean, because they both start with M, so we can know the difference. All right, so when it's symmetric, like I was showing you up above with dataset B, they're roughly the same. If we take the average for a symmetric distribution, if you imagine with this, we have all of these different data values in here, what we would do is add them up, divide by how many there are, and the mean would land at close to the same spot as the median. Very rarely will they be exactly the same, but the idea is with a symmetric distribution, whatever the median is, the mean should be close by. With the skewed left distribution, what we're getting are these outliers on this left-hand side. So it's kind of the opposite of what I did for dataset C, is that if we change this and just had a lot of extreme small values, but then most of our data was at the upper end, when we would take the average, we'd have these small values influencing our data. So it ends up happening to our mean, where we start with expecting it to be at the median, it gets pulled to the left-hand side, or rather, it gets skewed to the left. So that's part of this wording for a skewed distribution, is talking about the effect of the mean. And when we have these small outliers in this left tail, it's pulling the mean to the left-hand side. So maybe we'd be somewhere over there. So with the skewed left distribution, comparing the median and mean, the median's going to be larger than the mean for a skewed left distribution. Then similarly with skewed right, which is what happened with dataset C, we could see how it was pulled to a much larger value because of that outlier on the right-hand side. And when we have a skewed right distribution, we have these large values off to the right. So that mean is going to get pulled to the right-hand side. So our mean might be somewhere out there. So if we compare the median and mean, the median's going to be smaller than the mean. Now this can be helpful because maybe if you're looking at a histogram, it can be difficult to tell what shape the data is. Like maybe it looks skewed left, but you're not quite sure if it's symmetric. Well, what you could do is grab the values for median and mean and see which relationship comes through. Are they relatively close to each other? Is the median much larger than the mean? And that can support the naming of the shape of the distribution. So with that, let's look at this graph for for box office earnings from Hollywood movies. So what we have here is different box office earnings from $0 up to $1,200. I can't remember the units, and I can't even think of the scale right now of what box office earnings would be. Would it be thousands, millions? They make a ton of money. So anyway, down here on the right-hand side, that's where we can see most films. Most films that come out would behave down on this lower end. We have a few films that do a bit better, but then we want to pay attention to these 3 films out here that are much larger. What I would think for those films that had very high box office earnings is those are probably films that are sequels or have a strong following. Maybe it's an adaptation of a book with a really large following. In fact, I remember from this data set, I know this film all the way to the right-hand side was the last Harry Potter film. That's the one that's out there. So huge following. It was the last film. So it behaved very differently than most of the data. And then I think this was like a Pirates of the Caribbean and a Transformers movie or something like that. But the idea is that we have these outliers out here, and those are coming from these blockbuster films. So let's talk about center of the graph. So what I want to get at is expected value. So if I think about what are the expected box office earnings for a film, well, in terms of expected box office earnings, we have median and mean to work as the idea of center or central tendency. So median, I could kind of estimate where the peak of the graph is. So maybe here-ish would be the median. Let's say that's at about 50. If we took the mean, well, we have this right skewed graph here. We have these outliers in that right tail. So with the right skewed graph, the mean gets pulled to the right. So let's say my mean ends up, and I'm just guessing here, but let's say it ends up at about 200. So we have these two different measurements for center. And if I'm trying to answer this question of expected box office earnings, a random person makes a film, what can they expect to take home from the box office? Well, we'd want to figure out which would be better. If I use the mean, it's taking into account these movies out here, which have very different characteristics from a random film produced that year. So we don't really want to have these as part of the data because they're doing their own thing. It's a very specific thing that's happening with those. Whereas the median ignores those values. Like I showed up above there was how changing those outliers at the end didn't change the median, kind of get covered up the same way as any other numbers would. So in this case, our median would be the best measurement for expected value. Talking about a random film coming out that year and what happened or what could we expect to happen, we would say about 50, because then that would ignore these extreme values that just don't line up with the other films. So with this, we get this idea that the median is resistant to outliers. So the value of the median isn't being influenced by these extreme numbers coming through, whereas the mean is not. So with this, the mean is skewed to the right by those outliers. And with that, when our mean is skewed, it makes it not an accurate measure of center. Instead, the median is what we'd want to use. So what this leads us to is that if we know the shape of the data, what measure of center do we want to use for expected value? When the data is symmetric, they're basically the same, and if we can use the mean, it's an accurate measure of center and it takes into account the actual values coming through. So when we have a symmetric distribution, we'll want to describe the center using the mean, but with the skewed distributions, we can't really trust that mean because it's being pushed and pulled by our outliers. So what we'll want to use is the median to describe center. So that's this little chart I have at the end here, is when we start to make these descriptions for data, if it's skewed, for center we'll want to talk about median. Spread, we'll use this thing called interquartile range, which we'll talk about in a future video. If the data is symmetric, we'll want to talk about mean for center and standard deviation for spread, which we'll talk about standard deviation in the next video. But we end up with these kind of two branches of how we want to describe center and spread based on the shape of the data, and mostly with the fact that if the data is skewed, then mean and standard deviation will be skewed and no longer become accurate measurements. But if they're symmetrical, then we can use those two values.